The gradual shape memory effect, exploring multiple shape transformations in smart materials. Have you ever wondered what would happen if the materials around us actually possessed a memory, and not just a simple memory of one shape, but the ability to remember a whole sequence along a timeline, transforming step by step, kind of like choreographed dancers? Welcome to this explainer. Let's jump right in and explore how completely passive materials are becoming programmable, multi-step machines.
Okay, let's dive into this because this isn't CGI. This is a real, totally mind-bending phenomenon in action. What we're looking at is a programmed beam made of a shape-memory hybrid material, and it's being immersed in hot water. But watch closely. It doesn't just snap from point A straight to point B. Notice how it actually bends downward first, holds that position for a sec, and then, as the process keeps going, it bends entirely upward. We call this the triple shape memory effect. Instead of just remembering where it started, it remembers a highly specific, distinct intermediate stop along the way. I mean, you are literally watching a piece of plastic perform a carefully planned, multi-stage routine. How cool is that?
So let's nail down exactly what we're talking about here. The multiple shape memory effect is essentially the ability of a programmed material to hold one or more well-controlled intermediate shapes during its recovery from a temporary shape back to its original form. Think of it kind of like a save state in a video game, right? Or maybe setting a waypoint on your GPS app. The material literally pauses at these programmed waypoints before it reaches its final destination. In your standard run-of-the-mill dual-shape memory effect, you heat a material up, deform it, cool it down to lock in that single temporary shape, and boom, upon reheating, it snaps right back to the start. But with this multiple shape effect, we're adding these incredibly stable intermediate forms into the recovery phase, which opens the door for some seriously complex, timed movements.
Now, if we look at the academic history of all this, it's pretty fascinating to see how discoveries evolve across completely different disciplines. The specific term multiple shape memory effect, that was actually born and coined over in the shape memory polymer field. This happened when researchers started designing these complex, multi-layered polymers with multiple transition segments physically built into their chemistry. But, and this is key, similar phenomena were actually reported much earlier in the shape memory alloy field. Metallic alloys showing a two-way memory, or gradually changing shapes through temperature gradients. Researchers have been studying that for decades. So while the polymer chemists definitely give us the catchy terminology we use today, the alloy metallurgists were already seeing distinct echoes of this multi-step behavior way earlier in their own work. Okay, so how exactly do we choreograph this multi-step transformation? Well, there are three primary mechanisms to pull off this multiple shape memory. First up, we can use materials that have multiple phase transitions intrinsically built right into their chemical structure. Basically, different microscopic parts of the material naturally melt or soften at different temperatures. Second, we can apply local or global treatments during the programming phase. Essentially, this means physically treating different zones of the material with varying levels of stress or heat so they react at different times later on. And third, we can use applied stimulus fields, like exposing the material to a gradient of varying temperatures or chemicals. By pulling these three specific levers, engineers can dictate exactly how and exactly when a material changes its shape.
And this brilliantly illustrates how these local treatments and stimuli actually work in practice. Check out this polyurethane shape memory polymer wire straightening out step by step, starting from the bottom and moving all the way to the top. So how is this localized control achieved? Well, they used a local treatment, specifically varying the water immersion times. The bottom part of the wire was left in water for a long time, right? It absorbed into the polymer and dropped its transition temperature significantly. The middle part got less time in the water, and the top was kept completely dry. When you gradually heat that entire wire, this gradient setup dictates that the bottom recovers first, then the middle, and finally the top. The end result is this beautifully controlled sequential shape recovery.
When we compare the two absolute heavyweights of the shape memory world, polymers and alloys, we actually see a pretty stark difference in their natural talents for this choreography. Shape memory polymers, or SMPs, just have an innate talent here. Because of the broad temperature ranges over which they soften, most polymers can intrinsically achieve at least one intermediate shape during recovery. It makes them highly versatile. On the flip side, shape memory alloys, SMAs, are way more rigid in their crystalline behavior. Only a select few, highly specialized and intensely programmed alloys can pull off even a single intermediate shape. So rule of thumb, if you're looking to design complex, multi-step transformations, polymers are almost always going to be your go-to material.
Which brings us to a really profound realization, and I think it's perfectly captured by this quote from researchers in the field. The material is the machine. With this multiple shape memory superpower, we aren't relying on external motors or gears, pulleys, or complex electronic circuits to create sequential movement anymore. The passive material itself has literally been transformed into an active, programmable machine. The code for how it's going to move is written directly into its physical and chemical structure. And the execution of that code, it's triggered simply by applying an environmental change, like heat, water, or light. It's a total game changer.
So you might be asking, why does this all matter? I mean, sure, shape-shifting toys and self-assembling structural games are super fascinating, but the real groundbreaking applications, the ones that are genuinely revolutionary and life-saving, are happening right now in the medical field. We are talking about devices that can navigate the complex, delicate pathways of the human body, change shape to perform a really crucial medical function, and then change shape again to be safely removed or even dissolved. Let's look at some real-world clinical examples that are actively transforming patient care.
Now, what's really interesting about this slide is how this concept completely solves a massive problem in minimally invasive surgery. What we have here is a retractable stent made of a polyurethane shape memory polymer. It starts off tightly compacted, right? So it can be pushed through a tiny, narrow catheter deep into the body. Once it hits the target location, boom, it deploys into that wide star shape to hold the vessel open. But here is the absolute magic. Over time, as it sits in the body and absorbs water, that moisture acts as a chemical stimulus. The stent naturally shrinks back down, retracting into a much smaller circular shape. This means that if the stent is only needed temporarily, it's already shrunk itself down. It makes it incredibly easy to just pull back out without scraping or damaging any of that delicate tissue.
Let's move to and see how this builds into even more advanced designs. Take a look at this retractable shape memory hybrid stent. Instead of relying on just one material absorbing water, this is made of two entirely different parts. You've got an elastic silicone component that naturally wants to stay small, and a rigid transition component, something like sodium acetate trihydrate, that locks it into that large expanded star shape. But once it's inside the body, that rigid transition component gradually dissolves in the surrounding aqueous bodily fluids. As it literally melts away, the elastic silicone is freed from its constraints and safely returns to its original, much smaller shape. It's a medical device that dismantles its own structural support on command, using the body's natural environment as the trigger. Absolutely brilliant.
So the crucial point is that we are entering this incredible new era of self-installing and self-dismantling medical devices. Think about what this actually means for a patient on the table. Traditionally, placing a temporary stent, a surgical staple, or even an orthodontic brace requires one procedure to put it in and a second, often painful and highly invasive procedure to take it out. But these programmable, multiple-shape memory materials, they save patients from the trauma, the risk of infection, and the huge financial cost of that second surgery. They do their job perfectly, and then they just gracefully pack themselves up when their job is done.
Which leaves us with a truly exciting prospect to think about as we wrap up. If our medical stents, our surgical staples, and even targeted drug delivery systems can reshape themselves on command, adapting and reacting sequentially to their environment without a single motor or computer chip, what other parts of our world will these programmable materials transform next? From self-deploying structures in aerospace down to everyday consumer products that just naturally adapt to our needs, the potential is literally limited only by our imagination. Thank you so much for joining me for this explainer, and keep wondering about the incredible materials that make up our world.